If you haven't done so yet, please pause the video and try to solve the question on your own before listening on. What we can do first to begin solving the question is to write out the given quantities. Now, although the question says that the disk starts from rest, it then goes on to tell us that we had an angular speed of 10 revolutions per second and then another angular speed of 15 revolutions per second. So it makes the most sense, at least for part A, to say that the initial angular speed is the 10 revolutions per second, and then the final angular speed is 15 revolutions per second. And then we were also told that the angular displacement was 60 revolutions. And for part A, we're being asked to calculate the angular acceleration. And so to find that, we can turn to one of our equations from rotational kinematics. Let's take a look at those equations. There are several from which to choose, so you might want to pause the video and see if you can pick the corresponding equation that's going to allow us to solve for alpha. But after studying the equations, you should note that the third equation will be successful in helping us to calculate alpha. Why don't we take that equation and solve for alpha first? And of course, to do that, we could first subtract the initial angular speed squared term, and then divide both sides by 2 times the angular displacement. Note that the angular displacement is actually denoted as delta theta, and we had only written theta, so just a minor correction there. Now that we've solved for alpha, we can plug in all the known values. And when we simplify that, we get approximately 1.04 for the value. As far as the unit is concerned, since we plugged in values of revolutions per second, as well as revolutions, then the unit of the angular acceleration will come out to revolutions per second squared. That's actually not the standard unit, but again, since we plugged in revolutions, that's what we'll end up with. The usual standard unit is actually radians per second squared, but this would be the correct answer to part A. For part B, to find the time required to complete the 60 revolutions, we can actually turn to the fourth equation from rotational kinematics. So we'll write it down and then solve for t. So why don't we multiply both sides of the equation by 2, and then divide both sides by the term in parentheses. And then once again, we'll plug in the known values. And when we simplify that, we get approximately 4.8 seconds. So this would be the correct answer to part B of the question. Now for part C, we're being asked to calculate the time required to reach the 10 revolution per second angular speed. The fact that they're asking us to find that particular time to reach 10 revolutions per second suggests that the final angular velocity in this problem should be represented with the 10 revolutions per second. The initial would be from when the disk had started from rest. So in other words, we can write 0 revolutions per second for the initial. Let's also recall that we determined the angular acceleration earlier in the problem to be the 1.04 revolutions per second squared, and now we're looking for a time t. So once again, pause the video and see if you can find the correct equation to use to find t. And in this case, it turns out to be the first equation, so we'll write it down and solve for t. We'll subtract both sides by omega naught, and then divide both sides by alpha. We'll plug in the known values, and we can see that we get approximately 9.6 seconds for the time. So this is the correct answer to part C. Finally, for part D, to calculate the number of revolutions from rest until the time the disk reaches 10 revolutions per second, notice again we're using the same parameters that were just used in part C of the question, but this time we're being asked to calculate the number of revolutions. So we're looking for the delta theta. And really any of these equations I think could be used, well, at least the ones that include delta theta, of course. Why don't we just arbitrarily pick this equation since we have already used it in the question. And then we've already solved that one for delta theta earlier, so let's just write that result down. And then we'll plug in the known values. And once we evaluate that, we should get approximately 48 for the value of delta theta. Notice that the unit is going to be in revolutions, not the standard unit of radians. And that's because, again, the values that we're plugging in are all in terms of revolutions. So just make sure that you note the correct unit. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon and also subscribe to the channel. Remember that you can send in your own question to this email address and I will do my best to answer it on YouTube.